F325, Christmas mock, December 2013, chemistry. I'm going to use this video to go through the answers to each question step by step. Things you should know about this mock are that it's made of past exam questions from various places, not all OCR. Some of them are legacy questions, some of them are from different exam boards. In terms of the level of demand and difficulty, this is around about what you should expect from an F325 paper. The only difference being that we haven't included any transition metal questions, therefore it's a little bit shorter than an actual F325 exam. F325 Christmas mock, question 1. I'm going to start off by looking at this question, which is a rates question. Typical for F325, it's got a wordy introduction that doesn't really contain anything of what we need to answer the question. So I'm going to go straight down to this table here, which contains some initial rates data. Underneath the table, we find the things that we actually need to do to answer the question. So we've got to write a rate equation, calculate a rate constant, write some units, and we've also got quality of written communication mark. Total for this question is 6. So I'm going to start off by working out the order for each of the reactants. So I'm going to start off with ClO2. For that I'm going to use experiments 1 and 3, because between those two experiments ClO2 increases by 3 and the rate increases by 9, which is of course 3 squared. So once I've determined that, I'm then going to need to write a sentence to explain what is happening. Feel free to pause the video here if you want to have a go at this yourself. What I'm going to write is this. Okay, so that's going to be my sentence. I've got to say which experiments I'm using because that will be part of the quality of written communication. I've said what's happening to the concentration and I've said what's happening to the rate. The order for this is second, and I'll get a mark for writing that sentence. So once I've dealt with ClO2, I'm then going to need to do the same thing for OH-. So for OH-, I'm going to use experiments 1 and 2 because ClO2 stays the same. OH- increases by 2.5. Now look at what's happening to the rate. That's also increasing by 2.5, so then I'm going to need to write another sentence to go with that. Feel free to pause the video if you want to have a go at that yourself. My sentence will say this. Okay, so that's my second sentence. And again for that, I'm going to get 1 mark. So now that I've done the orders of reaction, I'm then going to go into the next bit, which was asking me to calculate the rate constant and write a rate equation. So I'm going to start off by writing my rate equation, which goes like this. K is my rate constant. ClO2 is second order, so that needs to be squared. Okay, that's my rate equation. I'll get a mark for writing that. Then to calculate the rate constant, I'm going to need to rearrange that equation. So I've got K equals rate divided by Next I'm going to substitute in my numbers, so I'm going to use the numbers from the first row in the table, because that's easy enough to do. And when I put that into my calculator, I should get an answer of 200, which gives me mark number 4. And finally, units. Okay, if I look at my original rate equation here, I've got moles per decimetre per second over 3 lots of moles per decimetre. So if I was to cancel that down, then I would get moles squared dm to minus 6 seconds to minus 1. For that, I will get another mark. So that gives me 5 marks, and my quality for communication will be for saying which experiments, so between experiments 1 and 3 and between experiments 1 and 2. And that gives me my total of 6 for question 1A. Going on to part B. So it's asking us how the rate equation tells us that there's more than one step. And for this, we just need to say that change that to mole, because that's probably a better word to use. Okay, so rate equation only contains one lot of OH minus, because we've worked that out in part A, its first order. Whereas in this question here it says the balanced equation, we've got 2 ClO2 reacting with 2 OH minus, so the two don't match together. Okay, so we're saying rate equation only contains one lot of OH minus, balanced equation contains 2, so there's got to be another step that uses that second OH minus. B part 2, overall equation. I suppose this is a bit of a logic question. You've just got to look at your question. So we've got 2 ClO2, 2 lots of OH minus, and we get chlorate 3 ions, so we get ClO2 minus, and chlorate 5 ions, so that's this here. Hold on. So chlorate 5 ions, so we've got chlorine and oxygen. This is plus 5. It's going to have a minus charge because all chlorate ions have a minus charge. So if we think about how many oxygens do we need to make that plus 5 and leave a minus left over, and that is 3. So down in this equation, get back into that. Put that in there. And then it says aqueous solution, so presumably we're going to get some water as well. Let's see how that works out. So we've got 2 chlorines on the left, 2 on the right, 6 oxygens on the left, 6 on the right, 2 hydrogens on the left, 2 on the right. Done. So it'll be 1 for the correct species, because you've had to work out what the chlorate 5 ion is, and 1 for the balancing. Question 1 part C. What is the meaning of the term half-life? Okay, so that should be straightforward. It's a definition, you just need to learn it. Order of this reaction. Okay, so remember this is talking about this investigation that this student is doing. It says this reaction has a constant half-life, so that must mean that the order is first. Final part of question 1, so another student investigates a chemical reaction, and in this one she finds that the rate doesn't change when she changes the concentration, so that must mean that it's 0. Christmas mock, question 2. This is an acids question, and it's asking us about benzoic acid. Things to note, it's a weak acid. I've also got a pKa there, which means that eventually I'm going to have to convert that into a Ka value. Starting off with this simple question, conjugate base of benzoic acid. So what that's saying is that this is the acid. You should all know that an acid is a proton donor. So its conjugate base will be when it's lost its proton. All carboxylic acids lose that one there. So we're going to be left with C6H5COO minus. Part B. What is the meaning of the term pKa? Slightly misleading because you're all probably thinking that it's asking for a definition. It's not. It's actually asking for this calculation. Okay, that's the easy bit of this question over with. Part C is asking about the solubility of benzoic acid. So, first thing to look at is we've been given a concentration in grams per decimetre, which of course we don't work in grams per decimetre, we work in moles per decimetre, so we're going to need to convert that using our AS moles calculations. I'm going to do 3.4 divided by the MR benzoic acid to convert it from grams per decimetre into moles per decimetre. Slight disagreement with the mark scheme. I'm awarding a mark for this MR and a mark for correctly doing the calculation there. Okay, next thing, it's asking me to calculate the pH. Because this is a weak acid, okay, we've not had any mention of buffers, just weak acid, so I can use the square root calculation. So that means that I'm now going to have to work out Ka, because at the top I've been given pKa, so I'm going to do 10 to the minus pKa. Okay, at the top of the page, pK is 4.2, so I'm going to do that calculation there, which gives me 6.31 10 to the minus 5. Now I'm going to sub that back into this calculation here. And when I work that out, I get right, so marks so far I'm going to get one for calculating Ka and one for calculating H+. Final step, pH equals minus log H+, so minus log put that into my calculator and I will get 2.88. 1 mark for that final answer. Part D. This was your stretch and challenge part of the paper, because obviously you're not yet familiar with benzene. Okay, benzene dicarboxylic acid looks like this. 2 pKa values, so they're going to correspond to the 2 acidic hydrogens that it can lose. So it's lost one there. And in the second stage, it's going to lose the second acidic hydrogen. Okay, 1 mark for each equation. And then finally part E, so this is a buffers question, it's out of 9. Can be quite overfacing to look at because of all the lines, large number of marks that goes with it. However, it's actually quite a nice question. So we're going to start off with, state what a buffer solution is. So it's a system that minimises changes in pH, 1 mark for saying that bit. On the and 1 mark for saying the second bit. So a system that minimises changes in pH on the addition of small amounts of acid or alkali. Then it says, explain how this solution acts as a buffer solution. Okay, so we're going to start off by working out what the buffer is. Okay, so it says here we've got benzoic acid and sodium benzoate. So it's the benzoate bit that we're interested in. So C6H5COOH. Okay, that's our buffer equation. Quite often you'll get a mark for this in this question, you don't. What you do get marks for in this question are what happens when you add acid and when you add alkali. So if you add acid to this, so that's the acid, it's going to react with this. We're going to get a mark for that equation. You also need to say what happens to the equilibrium. Okay, if we're making this, that means that this buffer solution has shifted left. So 1 mark for that. And we've got what happens when we add alkali. So there's the alkali. That's going to react with H+. So 1 mark for the equation. And again, equilibrium. Okay, then removing H+, then this equilibrium system is going to shift right to restore it. So equilibrium shifts right. 1 mark there. Okay, once we've done that, we've done the first bullet point. Now it says calculate the pH of this buffer solution. Okay, because it's a buffer solution, we need to work out H+. As it's a buffer, the only way that we can use that is to use the Ka expression. Rearrange it. Okay, so that's the equation I'm going to use, and then I'm going to sub in my numbers. So Ka comes from a previous part of this question. Concentration of the acid is up at the top of this question, it's there. Concentration of the salt is also given at the top, that's here. Work that out and I get this. The final step . Okay, so marks awarded in this question then, as we said, it's out of 9, no quality written communication. So just for the buffer bit we've got 6 marks, so that means there's 3 down here. So it's 1 for your final answer here, 1 for your H plus, and it will be 1 for the rearrangement of this equation. Christmas mark, question 3. Again, this is an acids question. However, this is a strong acids question, and we've got titration curve in there. Okay, so it's talking about nitric acid reacting with ammonia, and we've got a titration curve for that happening at the bottom. It says to reduce the concentration of the nitric acid. Lots of people will be trying to do all manner of different complicated calculations here. All we need to look at is the fact that this starts at pH 1. If we know the pH, then we can get H plus by doing 10 to the minus pH equals 10 to the minus 1. Just to reiterate, nitric acid is a strong acid, therefore the concentration of the acid is equal to the concentration of H+. So the concentration of the acid is this. How can we tell from the pH curve that ammonia is a weak base? You need to look up here. This finishes at about pH 11. That's all we need to say. Next part of this question is about indicators. So we've got 4 indicators to choose from with a pH range. We need to look at these pH ranges on the titration curve of the previous section. I'm going to go for this one because I know it's the right one. So if we go back over to this curve, it changed between 3.8 and 6.7. That's definitely in the vertical section of this curve. If you were to check any of the others, you would find that they are not in the vertical section, or they might be on the edge of it, but also where it's slightly curving off. So the answer is rhesus urine. Final bit of this question. Lots of people found this difficult. So it was repeated using ammonia with twice the concentration. Again, I'm going to go back to the titration curve. This titration curve finished at 25. If I use double the concentration, then the end point will be half as much. And then because it's more concentrated ammonia, the final pH will be slightly higher. Christmas mock question 4. Question 4 is part of the electrode potentials topic. We've got 2 equations. First bit's relatively straightforward. Which one does not involve a redox reaction? So for that you're going to have to work out oxidation states. So you've got +6 for the chromium here. This one is +6. Oxygen there is -2. That's -2 + 1. -2 + 1 -2. And this one we've got +6 and +3. So we've got a change. We know it's not equation B. So it's equation A. No change in oxidation states. Okay. Effect of adding acid to the equilibrium shown in equation A. So if I'm going to add acid to this first equation, let's just clear this up a little bit. Right, so equation A, I'm going to add acid. Acid's going to react with the OH minus. If I'm removing the OH minus, then this equation is going to try and shift to replace the OH minus to oppose the change. So the effect is that it's going to shift left. Okay, so I said left, I'll get a mark for that. The reason being, H plus reacts to that OH minus, so the equilibrium is going to shift left to restore the OH minus. Okay, part C, lots of people found this very difficult. This is a moles question. So we've got 1.20 gram sample of iron wire reacted with some acid. All that's going to do is react it and dissolve it into solution. Solution was transferred into a volumetric flask and made up to 250 centimetres, so that number is going to be important. And we're titrating 25 centimetres of that. What we're reacting it with is dichromate. I use 23.2 centimetres of this concentration dichromate. So we're going to start off working out moles of dichromate by using, so we've got 0.0150 and gives us okay, so that's our moles of dichromate. 1 mark there for that. Again, if you're going through a paper like this and you look at this question and you don't know anything else that you can do about it, then you could at least look at this and think, right, I could do n equals CV over 1000 and get the mark for the moles on this. Next thing we're going to do is we're going to work out the number of moles of iron 2 plus in 25 centimetres cubed. So for that, I'm going to look up here because this is the equation I'm dealing with. There's the iron 2 plus, there's the dichromate, and the ratio is 1 to 6. So I'm going to do okay, so I've got my moles of Fe2 plus, but that is of course in 25 centimetres cubed. Okay, so to get the amount in 250, I'm going to multiply that by 10. And then I'm going to need to convert that into mass. Okay, so that is the that is the mass of iron in the iron wire. I'm told up at the top here that the mass of the wire is 1.2. So now I need to know what percentage of that 1.2 is actually iron. So the percentage is 1.17 divided by 1.2, and the answer is, and that's our final mark. F325 Christmas mock question 5. So again, another electropotentials question. We've got the definition of standard electropotential. Again, 10%ish of your paper will be on definitions. This one is the EMF of a half cell compared to the hydrogen reference electrode. Underneath that, we've got a diagram to draw for showing how we would measure the standard electropotential. So because it's the standard electropotential, it will be connected to the hydrogen half cell, which you should all know how to draw. because Cl2 is also a gas, we're using a gas electrode on this side. Okay, marks in this question. One for the salt bridge and the voltmeter. One for both my gases being at 1 atmosphere. One for both platinum electrodes. One for both concentrations being a mole per decimeter. And the final one that everybody missed, because it says conditions, I have to also state the temperature. And that will be my 5th mark. Part C is asking me to combine 2 equations. So the 2 relevant equations from the previous page are these. And this one. Okay, so they are the 2 half equations that I'm dealing with. This one's the more positive, so that's going to go forwards. This one's going to go backwards, so it's going to change to this. And the overall equation, I'm also going to need to multiply this one by 2 to get the electrons up to 10. And this one by 5. And then when I add those together, I'm going to get and I could also write those together, so that's going to be 6. Ideally, what I need to do finally is to cancel that all down because it all divides by 2, so I will have and that should be my final answer. Standard cell potential for a cell with this overall reaction, so it's the positive cell take away negative cell, gives me 0.45 volts. And then finally, how can you tell its reaction is spontaneous? Because the cell potential is positive. Christmas mock question 6. Question 6 is a Born-Haber cycle question. We're given a cycle and all we need to do is put the numbers in the correct place. So if we look at what's going on here, we've got 2 elements forming a solid, so that's the enthalpy of formation, which is minus 416. On this we've got sodium solid turning to sodium gas, so we're looking for the atomisation of sodium, which is plus 109. Next line we've got oxygen stays the same, sodium turns from Na into Na+, so that is the first ionisation energy of sodium, which is plus 495. Next line we've got half an O2 turning into O, so that is the atomisation energy of oxygen, which is plus 247. Here we've got oxygen turning into O-, so that's the first electron affinity, which is minus 141. The next one, we've got the second electron affinity, which is plus 791. And that should be all of our numbers filled in. On this cycle, we really need to show that here we've got 2 NAs, so we're going to do 2 times that number. 2 NAs there, so we're going to do 2 times that number, and it really is good practice to show that on your diagram. Then we've got to calculate the lattice enthalpy, so this is the missing one. That arrow's pointing down, so we're going to go anti-clockwise. So come to this arrow, which we're going against, so we're going to have minus 791. We're going against that arrow, so we're going to change the sign to plus 141. Going against this arrow, so it will be minus 247. Against that one, so it will be minus 2 times 495. Against this arrow, so minus 2 times 109. And then with that final arrow, so minus 416. Your final answer should be minus 2521. It's generally 1 mark for the minus sign and 1 mark for the number. Okay. Then we're going to move on to part C. So this is our comparison question. We've got 2 metals, so 2 cations to compare and 2 anions to compare. So we'll start with the cations. So we've got Ca2+. Lots of people talking about calcium and not mentioning that it's an ion. Okay, so those are the 2 things that we're going to say about cations. So calcium ion is smaller than the potassium ion. Calcium ion has a greater charge. Then we're going to compare the anions. So chloride, okay, marks in this bit. You'll get 1 for either one of them, 1 for this. Then we've got to say greatest attraction between one for that. And finally, and just remember when you're answering this question, you should follow the kind of standard answer of, oops, try not to write it in that. So we've got charge, radius, attraction, size. And we've got part D. So enthalpy of hydration of strontium. Strontium is in group 2. And it should start in the gas phase. Going to add some water to it and make it into Sr2+ aqueous. Then we've got magnesium sulfate, which is a solid. Add some water to it. There we go. And the very final bit. Okay, so the things that are going to decide if something dissolves or not. So think about your Born-Haber cycle. You've got lattice enthalpy on that side, and on this side you've got hydrations. Okay, so we've got lattice enthalpy, enthalpy of hydration, and enthalpy of solution. They're the things that decide whether something dissolves. Then we're going to say if right, so if lattice enthalpy is very exothermic, so if this arrow is really big, then solution will tend to be endothermic. Okay, remember endothermic generally is unfavourable. Then you've got to think to yourself, okay, if hydration is very exothermic, so now we're saying, right, what happens if this arrow is really big? Yep, so that means that solution will be exo. And then you've got to think, right, exothermic's favourable, so okay, so just run through that again. The three things that decide if something dissolves, you've got lattice enthalpy, enthalpy of hydration, enthalpy of solution. 1 mark for saying that. Then you've got if this arrow is very big, then the enthalpy of solution tends to be endothermic. Okay, so if this one's really big, then enthalpy of solution tends to be endothermic. So 1 mark for saying that. Draw that a little bit clearer. Next mark for saying, so there's your ions again, there's your lattice enthalpy. Next mark for saying if your hydration enthalpy is very exothermic, then enthalpy of solution tends to be exothermic to meet that. Okay, so 1 mark for saying that. And then the final bit is for saying the more exothermic something is, the more favourable it is. So if it's more exothermic, it's more likely to dissolve. So that's your final mark. Again, this is the hardest bit of this question. Very high level question at the end, towards the end of the paper, quite demanding. F325 Christmas mock question 7. Okay, final question on your paper is about KC. We've got starting off with asking us to calculate the concentration of ammonia at equilibrium. So to start off with, we'll write ourselves a Kc expression. Okay, so that's our first thing that we're going to write. Then we're going to need to rearrange this to give us ammonia. So we're going to do Kc times okay, that would equal NH3 squared, so we're going to square root all of that. If we sub all the numbers into that, so we've got Kc further up in this question. N2 1.2, H2 if we calculate that, you should get 0.876. So marks, we're going to get 1 for this expression, 1 for the rearrangement, and 1 for the answer. Underneath that we've got some questions about equilibrium. So, catalyst, you should all know, catalysts don't affect the position of equilibrium. They just change the rate. So we've got two things that it's asking us about: position of equilibrium and equilibrium constant, so Kc. Okay, so catalyst doesn't affect either of those things. Lots of people that I marked, I was noticing that they were either only mentioning Kc or only mentioning the position of equilibrium. Question clearly asks about both. There's 2 marks, that's 1 for each thing. Okay, if we increase the temperature, so for now we're going to need to look at the equation at the top. This reaction is exothermic, so if you increase the temperature, it's going to drive it in the endothermic direction, which is left. So equilibrium, left. Okay, it's going to go backwards because the backwards direction is endothermic. Kc, if equilibrium shifts left, then Kc decreases. The last bit, pressure is decreased to 50 atmospheres. So again, let's look up at the top. We've got 4 moles on the left, 2 on the right. So if it's decreasing, it's going to go to the side with most moles. So equilibrium shifts left. Kc, because it's pressure, there's no change. Because the only thing that affects Kc is temperature. Final bit of this question is about entropy. In entropy questions, you pretty much always get 1 mark for stating the equation. Okay, you will also in this question get 1 mark for converting the temperature into Kelvin. Then we're going to sub everything into the equation. So delta H is minus 92, which was right at the start of the question. Temperature 773, and we're going to do minus 198.6, but that must be divided by 1000. Gives us a final answer of plus 61.5. So we're going to get 1 for remembering to divide by 1000 here, and 1 for the final answer. And then the final bit, limitations about using this. So 1, enthalpy or entropy may so you've got to remember the entropy value that you quoted here and the enthalpy value that you quoted at the start are both measured under standard conditions, so they might be different at 500 degrees. And 1 mark for saying conditions might be and that is the end of the test.